an assessment, but rather how right was Landau, like a sort of shocked appreciation. Yeah, so I tried to put the bold there. So I'm going to start with a sort of manifesto for this program, and intersperse in that discussion some what I think are some new observations, and then this will lead to a sort of extended application of this point of view, which is at least conjecturally actually holographic. Okay, so you might say, well, why do we need a campaign to rehabilitate the reputation of Landau? And I guess we really don't. But what I mean by that is the following. So a way of thinking about phases of matter and transitions between them is by thinking about how they represent their symmetries. So this is a paradigm initiated by Landau, and I guess a more precise way to say that is phases of matter should be classified by what symmetries they break. And one way to think, one consequence of this is that gapless excitations in a phase, or degeneracy, ground state degeneracy in a phase, should arise as Goldstone modes for spontaneously broken symmetries, continuous or discrete, respectively. And combined with Wilson's insights, this leads to a sort of leads to the idea that gaplessness or degeneracy is something that needs to be explained. That there should be, if there's a gapless phase of sort of stable situation with gaplessness or degeneracy, then that should have an explanation, in particular along these lines. Well, there are some apparent exceptions to this point of view on phases of matter, and I guess the reason I say that it's a campaign to rehabilitate the reputation of Landau is that if you've been to any condensed matter talk, quantum condensed matter talk in the last, I don't know, however many years, many of them begin by saying, well, Landau's told us that we should classify phases by symmetry, but I'm here to tell you that he was wrong, and here's an example of a phase or a critical theory that's beyond Landau in some sense. And usually beyond Landau means something involving topology. So some examples of phases of matter which are beyond Landau in this sense is topological order. For example, the deconfined phase of Z2 lattice gauge theory, realized, for example, in an exactly solvable model in the toric code, depicted here, or fractional quantum Hall states, which are actually really exist in experiments, and even more familiar things like the Coulomb phase of electricity of E&M is a deconfined phase of a gauge theory, which is difficult to think about as a consequence of symmetries, at least had been. And then there's some more examples in red here, which I actually don't know how to explain in this way, and so I'm not going to say anything else about them. And this is fodder for the continuation of the program in the future. But these two examples, actually, it turns out we can understand completely within Landau's paradigm, and the basic reason for this is that we need to expand what we mean by symmetries. And so the thing that Landau called a symmetry is what we should actually call a zero form symmetry, where the conserved current in the case of a continuous symmetry is a one form, and the fact that it's divergence free means that there's a charge which is conserved, meaning that it's independent of what time slice you integrate it over. And I think it's a useful observation, even here, to notice that this is really a topological condition. It says that this quantity Q depends only on the topological class of this codimension 1 surface over which we integrate the charge density. And perhaps with that insight, one is led to generalize this idea to a current that has two indices, that is a two form, two antisymmetric indices, and its conservation, that is its divergence freeness in this sense, means that there's a thing, star J, that we can integrate over a codimension 2 slice of space-time, And its divergence freeness means that it only depends on the topological class of that codimension 2 object. So again, a topological condition. And in the case of ordinary symmetries, the objects that are charged into the symmetry are local operators. That's this kind of statement. In the case of one-form symmetries, the charge objects are instead loop operators. So the variation of a loop operator under this one-form symmetry generated by J, here Q is this charge, is again, it's linear in this charged operator, and its transformation only happens if it links with the curve, if the surface sigma links with the curve C. Go away, Dropbox. Okay, and a good example of this phenomenon is in ordinary Maxwell theory. If in ordinary Maxwell theory there is no charged matter, then F satisfies this condition. This is just Maxwell's equations without any charged matter. The charged objects are Wilson loops, and even if there is charged matter, there's a one-form symmetry in Maxwell theory, whose current is star F, and the charged objects. So that this is conserved by the Bianchi identity, that is the absence of magnetic monopoles, and the charged objects are the 't Hooft loops, that is the Wilson lines of the dual gauge field. And we can also define finite transformations in each of these cases. So here, in the ordinary one-form case, you just exponentiate the charge. We can do the same thing in the one-form case. And the poetical description of what it means to have a conserved zero-form charge, if the charge is carried by particles, is that their world lines can't end. The only way they can end is by being created and annihilated by charged operators. And in the one-form case, that's the statement that there are some string world sheets that can't end, except again on charged operators, which create those closed strings. And in both cases, we can have a discrete version where in fact there's no current, but there's still a charge. The consequence of that is that the particles can disappear in groups of K, and in the one-form case, it says that the strings can disappear or end in groups of K. Okay, so by the way, I hope you won't feel timid about asking questions. I'm not going to see if you raise your hand, so please just unmute yourself and ask. Okay, and so how does this lead to classifications of phases of matter? Well, just as in the zero-form case, the symmetry can be unbroken or broken, and it'll be useful to remind ourselves or to describe in a certain way what it means to not break or break a zero-form symmetry. So in the unbroken phase, the signature of this is that correlations of charged operators are short-ranged and decay as the charge object grows. So what I mean by a charged object in the case of a zero-form symmetry is a zero sphere. A zero sphere is 2 points, right? X squared equals 1. And so the charged object is just this two-point function. And by the size of the charged object, I just mean it's the separation between the two charged insertions. And in the case of a one-form symmetry, in this language it's exactly the same. The symmetry is unbroken when correlations of charged operators are short-ranged, and decay when the charged object grows. The charged object is now a loop operator, and this is the statement that it satisfies an area law. So in the case of ordinary E&M, the area law phase for this electric loop is the superconducting phase, where the photon is gapped. And okay, so the broken phase for a zero-form symmetry says that the 2-point function, let's say the 1-point function of this zero sphere excitation doesn't fall off as we make the zero sphere large. That is, there's a piece which is independent of the separation. And in the one-form case, that's the statement that the Wilson loop satisfies the perimeter law. And this is the same as not falling off as the loop grows, because we can add counterterms which are local along the curve, and to remove this dependence on the perimeter, that is just an integral along the curve, we can redefine the operator by such a factor. And so this is the statement that the large loop has a vacuum expectation value. And okay, so some consequences of what does it mean to spontaneously break a higher form symmetry. In the case of a discrete higher form symmetry, I claim that this is really basically by definition what it means to have topological order. I didn't define it earlier. What I mean by topological order is degenerate ground states which are locally indistinguishable. Locally indistinguishable means that no local operator mixes those ground states. In order to get from one topologically degenerate ground state to another one, you have to act with some non-local extended operator, exactly the kind of operators that generate a one-form symmetry group, or a p-form symmetry group with p bigger than 0. And the statement that that symmetry group is spontaneously broken is exactly the statement that that algebra of loop operators is acts on the ground state in a way that doesn't give back the ground state. It says that the ground state is taken by these the symmetry generators to another ground state. So that's exactly what we mean by topological order. And so two examples of this. Maybe the slide is a little too busy, but let me just highlight what I'm trying to say here. So one example is ZN gauge theory, or the Torah code. A description in this language of that is in D spacetime dimensions, is to say that it has a ZK one-form symmetry and a ZK D-2 form symmetry, which are represented by unitary operators. This is the one-form symmetry. That is, it's given a curve, we get an element of the group, which is just ZK. And here, given this represents the D-2 form symmetry. Given a D-2 manifold in the spacetime, we get an element of ZK. And if these guys satisfy this algebra, U times N is a root of unity. U times V is a root of unity times V times U. And the root of unity is not 1 if the curve and the D-2 manifold intersect. Rather, if they're linked is what I mean by that number. Then this is exactly the algebra of electric flux and magnetic flux surfaces in ZK gauge theory. And maybe a more familiar realization of this is in terms of BF theory, where the action for a dynamical D-2 form and a dynamical gauge field is this generalization of the Chern-Simons action, and U and V are realized as the Wilson loop and this generalized surface operator for those two states.
John, a quick question, just to keep it light. Yeah. But you know, I am by training condensed matter physicist, and I learned a long time ago that to figure out topological order of this kind, right, you have to throw loops around Tori, etc. So in this regard, I don't think it's new, right? It's something that is somehow
sure.
New, except that condensed matter physicists have a big trouble understanding two forms and higher forms. You don't learn it. I learned it via string theory and even employed it in a different context.
I agree. I think many people have appreciated this fact. Yeah, I guess that actually this is the fact I think that was first pointed out by Nusanov and Ortiz sometime in the
so Nusanov is my former postdoc, and it was kind of surprising, but on a more general level, right? It's a complete standard thing, right, to throw loops around Tori to figure out whether you have topological order or not, right? It's sort of
sure, yeah.
The real canon of conventional topological order wisdoms of the deconfining kind, blah blah.
Well, I think the thing I want to emphasize, I agree. So far, what I'm saying is not. I don't want to take credit for this observation.
But
I want to emphasize that it can be understood from the point of view of symmetries.
I appreciate that. I learned them. I know where you're going.
Good.
The complicated problem is condensed matter physicists, right? Because they have no clue what you mean with a two form.
Many of them have learned by now.
By now, perhaps, yeah, because of you guys, I guess.
I don't know. So another example that Jan will surely agree with is that we can understand fractional quantum Hall states, abelian fractional quantum Hall states, for example, in this language as saying that there's a ZK1 form symmetry. This is in D equals 2 plus 1, where the generators actually have a slightly twisted algebra, which you could think of as a consequence of a 't anomaly, which is the statement that the flux carries charge. And this algebra realized, the smallest representation of this algebra is k-dimensional, and those are the k ground states of the Laughlin state on a torus. I think actually it's not entirely clear whether we can understand the most general topologically ordered state in this language. I don't want to get into that in any detail, but at least it's certainly a useful language for understanding many examples. Okay, so perhaps a more ambitious application of this point of view is to think about the case where the one form symmetry is continuous. So, and the claim is that the gaplessness of the photon, even in the real world, can be understood as required by the spontaneous breaking of a U1 one form symmetry. And so exactly the one that I mentioned earlier. And so one way to understand this is by analogy with the case of spontaneously breaking a U1 zero form symmetry. So one way to diagnose that is to couple it to a background gauge field. And you know, if I spontaneously break the symmetry that the background gauge field is coupled to, then I'll generate a mass term for that gauge field, or I guess this is the Anderson-Higgs mechanism. So I'll generate a term in the action which goes like a squared. But then if I demand gauge invariance, in order to make that gauge invariance, it requires that there's some mode that transforms nonlinearly to make this whole thing gauge invariant, such that the whole thing transforms, so that, you know, the Goldstone mode and A transform like this. This whole thing is invariant. And this is a global symmetry in the case when this parameter is closed, and voila, the Goldstone boson. In the case of a one-form symmetry, if we would couple it to a two-form background gauge field, and again, the sort of two-form generalization of the Meissner effect would say that there has to be a b-squared term in the action, and making that gauge invariant requires that we add to it some kind of one-form field, which now you see if I set b to 0, this is exactly the Maxwell action, and the role of the Maxwell coupling is played by the sort of stiffness of that spontaneous breaking. Okay, so here's a question that you might have upon hearing this explanation of why the photon is massless, which is in particle physics, we're used to the idea that when you have an emergent symmetry, which in particle physics is called that accidental, that means it's a symmetry which is not a symmetry because it's explicitly broken by some irrelevant operator. So that is, the action is some symmetric action plus a term which involves a charged operator. And that charge operator has some dimension, some mass dimension. I've put something in here to restore the dimensions. Okay, so there can be approximate symmetries, and approximate symmetries can also be spontaneously broken. And when they are spontaneously broken, they lead to not Goldstone bosons, but pseudo Goldstone bosons, where the mass of the would-be Goldstone boson isn't 0, but rather is proportional to this coupling that we added, which breaks the symmetry. And it's only massless in the limit when we take the scale at which the symmetry is broken all the way off to infinity. And so you might wonder, based on this point of view, does the, I said that this electric one-form symmetry is a symmetry in the absence of magnetic monopoles. And so does it mean that if somebody does find a magnetic monopole, or even if they don't find it, if they do exist with some very large mass, does that mean, since I'm claiming that the photon is a Goldstone boson for the symmetry, does that mean that the photon actually has a small mass, which is a consequence of this mass of the monopole? And the answer seems to be no. A cheap explanation for that no is by dimensional analysis. So if we ignore the mass of the electron, for example, take the mass of the electron to be infinity, I think 0 would also work, then the only scale in the problem is the mass of the monopole. But we need that the mass of the photon goes to 0 when the mass of the monopole goes to infinity. And so the mass of the monopole can't appear in the numerator of the photon mass, and then there's no other mass to make up the dimensions, and so it has to be 0. So this answer is a little bit cheap. Maybe we need a better answer. A slightly better answer is the claim that, so here, in order to break the symmetry, we had to add to the action charged operators. But the operators that are charged under a one-form symmetry are loop operators. They're not local operators at all, and we can't add non-local operators to the action, the end. That's also not entirely satisfying. Well, okay. It's at least sometimes correct, but yeah, we can do a little bit better. So to do a little bit better, let's think about the discrete analog. So in the case of, say, the toric code, this solvable limit of Z2 gauge theory, the discrete one-form symmetries are exact symmetries. You can write down the operators that generate them. They commute the Hamiltonian. But anywhere else in this deconfined phase, this broken phase of the Z2 one-form symmetry, they're emergent symmetries. They're explicitly broken by the lattice. That is, there's matter that allows the loops to break, but they're still spontaneously broken. And the fact that they're spontaneously broken means that they take, in the thermodynamic limit, they take ground states to other ground states. The topological order is exactly there, despite the fact that the symmetry is only approximate microscopically. And there's actually a rigorous proof of this in the discrete case using quasi-adiabatic continuation. Okay, so then emboldened by this, let's return to the continuous case. And something we can do to remove the distinction between zero-form symmetries and one-form symmetries is compactify the theory on a circle. So that is, identify one of the dimensions of space periodically. X is equivalent to x plus 2 pi r. And in that case, we can think about the limit where the circle is small, and we can decompose the 3 + 1 dimensional gauge field into its parts. There's a 2 + 1 dimensional gauge field, little a, which we can dualize in 3 dimensions to a scalar, a pseudoscalar, I guess. And there's also a scalar that comes from the holonomy of the gauge field around the compact direction. And so if we include electrically charged particles with some mass me in this theory, then their world lengths can wind around the circle, and they'll generate terms in the effective action that look like this. All right, so this, think of them as instantons with instanton action me times r plus this phase, plus the phase associated with their propagation through this background vector field. And this quantity is, so integral of a is what I call phi. So this is a cosine phi term, which if I expand this around small phi as a mass, it says that this phi excitation gets a mass. The sigma field is still massless so far. On the other hand, if we have magnetically charged particles in 3 + 1 dimensions, then these are point-like sources of magnetic flux. They're exactly the monopole instantons that Polyakov used to explain why three-dimensional U1 gauge theory confines. They generate exactly this kind of, a dilute gas of them generates this kind of cosine sigma potential, which says that the sigma field also gets a mass. But the important thing for our purposes here is how do these masses, the masses of the components of the photon, basically the two polarizations of the photon, how do they depend on the radius? So you can see that as I take the radius to infinity, the mass of both polarizations of the photon go to 0. To understand this a little better, we could have interpreted this circle that we just introduced as the thermal circle. So its radius is the inverse temperature. And notice that known forms of topological order in less than or equal to 3 + 1 dimensions have the property that at any finite temperature, they're actually smoothly connected to a product state, to the trivial phase. The topological order that we know about in 3 + 1 dimensions or fewer is a 0 temperature property. At any finite temperature, it goes away. And this argument is perfectly consistent with what we've just seen. If the one-form symmetry is emergent, as soon as there's a circle in the space-time, a mass is generated for the photon, or alternatively, the ground state degeneracy is lifted in the discrete case. On the other hand, there is stable topological order to finite temperature. In the Platonic sense, at least, the two-form toric code in 4 + 1 dimensions. So that is basically two-form gauge theory in 4 space dimensions. Exhibits a phase which has topological order at even at finite temperature below some critical temperature. And one way to think about that from this language is that a theory with a two-form symmetry, that theory has a two-form symmetry, if you put it on a circle, like the thermal circle, it still has a one-form symmetry, and that one-form symmetry can protect the degeneracy. So this transition at which this topological order is destroyed is an extremely interesting one, which arises by the proliferation of strings. It's something we should understand better. Okay, so I mentioned this appeal to locality. So I said we can't add non-local operators to the action. And the reason that this argument isn't entirely satisfying, I know maybe some of you find it satisfying. I think maybe if one lived their lives entirely in the continuum, they might like this argument. But if you've ever thought about any kind of lattice theory, such as lattice gauge theory.
Could I interrupt?
Yes, please.
Thanks. Sorry, just to make sure that I got the argument right, could you go over again why? So you started by saying if you have an emergent symmetry, then it will be explicitly broken by a relevant operator. Then if you spontaneously break it, the goldstones will have a small mass.
That's for zero-form symmetries, yes.
Yes. Could you just say again, like in a couple of sentences, why that's different for higher form symmetries?
Yeah. So right, exactly. So that's the point I'm trying to make. So I'm saying that unlike in the zero-form case where the goldstone gets a mass, in the one-form case, it's the goldstone is still exactly massless, even when the symmetry is emergent. And I'm not sure what the best explanation for this is. So I think probably this argument number 2 is morally correct. Sorry. The idea being that in order to explicitly break such a symmetry, you need to add non-local operators to the action. And you can't, well, in a continuum limit of a local field theory, there aren't any non-local operators in the action. So, but let me explain that a little bit more. That's what I was about to do. So I think this is maybe the most concise summary of the difference, right? So in the zero form case, the charge operators are local operators. You can add them to the action with impunity. In the one form case, the charged operators are loop operators. Let's just say it's difficult to add them to the action. And so let me explain. Oh, yeah, thank you for the question. Let me explain a little more what I mean by it's difficult to add them to the action. So on the lattice, we add loop operators to the action all the time. For example, the Wilson action for lattice gauge theory is a sum over small loops of products, of these loop operators. And the real question of whether the symmetry of what happens to the symmetry is as we coarse grain this lattice theory, do these loops become larger or smaller? Do they become point-like loops in the continuum, or do they grow as we coarse grain? And one way to think about this is, let's think about the case of a zero form symmetry. So start with, say, a CFT just for definiteness and perturb it by some charged operator of some definite dimension. Then one way to diagnose what happens in the infrared is to compute the partition function of the perturbed theory in perturbation theory and thus coupling. And in a CFT, we know how this behaves. It's some power law. We can do the integrals. And we encounter this expected dichotomy. If the operator is relevant, there's an infrared divergence. L is the size of the system. If the operator is irrelevant, there's an ultraviolet divergence. So that is, a relevant operator changes the infrared behavior. So we can try to imitate this argument in the case of this frightening thing, where we perturb the action by a sum of loop operators. Again, we can try to see how the partition function is perturbed. And so you see it's governed by this sum over loops of the expectation value of the loops. So to define that, let me make some assumptions. So the first assumption is I'm going to regulate that sum with say, a cubic lattice. I'm going to assume that we're in the broken phase, where there's a strict, oh, sorry, I meant strict perimeter law here. That word is wrong. Strict perimeter law. This goes like the length of loop. And I'm going to approximate the loops as independent. So I could do the sum. And the result of that, of this sum over all loops on the independent loops on the lattice, can be written as this integral. I won't explain exactly how to do that. It's not too bad. It's in Cardar's book, for example. And you see this quantity has some familiar, interesting features. So notice there's a critical value of t. T is this coefficient of the perimeter law, below which the sum over loops gives a finite answer. Basically, the argument of log is less than 1. Yep. And near this critical point, we can expand this thing, and it looks like this. So surely this is, everybody recognizes this as the world line partition function of a single particle of mass m. And so this is, and you see in this partition function here, we're basically exponentiating this quantity. So this is just a gas, a sum over a dilute gas of these charged particles. It's just the world line description of coupling the gauge field to a Higgs particle. And so now we understand the dichotomy about whether the loops get larger or smaller, in the sense that, well, this charged particle can condense. If it condenses, then it Higgses the gauge field. The photon is massive. And if it doesn't condense, then it doesn't affect the mass of the photon. So I think this is, how to say, a step towards a better understanding of this distinction between emergence of zero form symmetries and emergence of one form symmetries. Okay, so this, having maybe understood a little bit about this, we were slightly emboldened and tried to answer the following question. So theoretical apparatus that follows directly from this point of view on symmetries is mean field theory. It says, well, we'll find an order parameter for the symmetry that you're going to break and write a field theory for it. And so a natural question to ask is, what is the analog of that for one form symmetries? And being brave, Nabil and I decided to call this mean string field theory. And so here, you'll see why in a moment. So recall the ordinary case of, say, a U1 zero form symmetry. There's some order parameter that transforms linearly under that symmetry. and demanding locality in space and a derivative expansion of this mean field, the Landau, Ginzburg, and Wilson tell us that we should write an action like this. It's an expansion in powers of phi and derivatives of phi, and it's local in space. And one way to think about where this comes from is that it comes from a variational ansatz for the ground state as a product state. And this phi specifies the local state of the degree of freedom at each point.
John, can I interrupt for a second? You're
Please.
now traveling in a different direction. I still have a question regarding the previous part, right?
Okay.
So whether you have finite temperature order or not, right, is usually the usual deal with Merman, Wagner, what is it, Coleman, whatsoever, did the same thing, right? And there, in the modern way of doing it, is the first thing you do is try to identify the topological excitation associated with a particular order parameter and decide whether that thing is point-like or not at finite temperature, excuse me. And it's point-like, you will destroy the order at all finite temperatures. Can you discern something of that kind in your one-form symmetry business that takes the role of the disorder operator, of the topological operator, like a vortex for you one?
Yeah, that's exactly right. So the fact that it's a one-form symmetry that's being broken means that the defect, the excitation that carries the charge into the one-form symmetry, is a loop operator in space-time. So that means it's a particle.
It's a particle at finite temperature.
So that means that at finite temperature it can wind around the thermal circle, and exactly this kind of argument that I described.
Like a particle in what is 3D or something, in 3 space dimensions. Yes.
That's right. That's right. It's in this example, it's the monopole instanton.
Yes. Okay.
Yeah. Good. And indeed, the distinction with the two-form Tor code in 4+1 dimensions is that the defects are strings in that case rather than particles. Yeah. Good. Okay. So back to mean string field theory. So I hope this paragraph is uncontroversial. Here comes the brave part. So let's suppose we have an order parameter for a U1 one-form symmetry breaking. That is, it's a string field, right? It's a field that's supported on curves, and it transforms onto the one-form symmetry like this by a phase that comes from integrating. This lambda is the parameter, the analog of alpha. You have to integrate it over the curve in question. And if the thing we're going to try is demanding locality, not in ordinary space, but in loop space. And we're going to demand that there's a derivative expansion in terms of a certain area derivative introduced by Migdal, essentially. And so again, imitating the form of this action, there's a term that's something like a potential V of absolute value of psi. So you see absolute value of psi is invariant under this transformation. And then there's something like a kinetic term, which comes from this area derivative, which it adds a little bit to the loop in the mu nu plane. And we can assume that this potential again has this kind of expansion. And I want to think about this again as a variational statement that the ground state, we're making an ansatz for the ground state as a sum over loops. And this psi of c has something to do with the wave function of those loops, the amplitude with which those loops participate in the ground state. And so I think an achievable goal for this framework is to develop a sort of crude picture of the phase diagram and transitions between the phases, just as one does in ordinary zero-form mean field theory, but now for systems with one-form symmetries. And so far, so what can we do? Well, here's the equations of motion. Given an action, you should certainly try to find the equations of motion. And we can identify two kinds of phases, depending on the sign of this parameter r. R is the coefficient of the quadratic term and the potential. If r is positive, then basically the wave function wants to be 0. A slightly better ansatz is something like this. Say that the wave function is e to the minus beta area, where by area of C I mean the area of the minimal surface whose boundary is C. If there's no surface whose boundary is C, if C is non-contractible, then it's just 0. And plugging this into the equations of motion, we learn that beta is related to R. So in the limit of large R, this approximation is actually this ansatz solves the equations, and it gives an area law. So that's the unbroken phase. If we, sorry, I should have said if we make R negative, the strings want to condense. A state where the wave function is an approximately uniform superposition of loops is called a string condensed phase by Levin and Wen, and it's a description of the deconfined phase. And so to understand this phase, let's we know that the answer is going to be something like a perimeter law. So let's parameterize this string field in terms of things supported on the perimeter of the loop. There can be a line tension term, which will give the literal perimeter law. There can be a geometric term, a thing which well, it's going to be the gauge field. And then there can be all kinds of higher things involving more derivatives on the world line, which will turn out to give massive fields. If we assume that the world line tension has an expectation value, we can plug this back into the action. There's an extremum with in the limit where mu is large, where their loops are small, and this reproduces the Maxwell action for this gauge field with a tension that's determined, with a Maxwell coefficient that's determined by this term in the string field potential. And a small check that this logic is making some sense is that if we redo it for Zn one form symmetry, it gives back the BF theory of Zn gauge theory that I wrote earlier. So this is, how to say, there's a lot of things to worry about in this description. In particular, this integral over curves in the action is really pretty terrifying to me still. But I think it's at least a promising framework from which I think we can learn a bit more. In particular, we might hope to understand something about what its description of the critical point is, and perhaps something about the upper critical dimension. Okay, so this brings me to the second part of the Landau paradigm, which is that the idea that not only should we understand the phases in terms of symmetries, but we should also understand what are the critical degrees of freedom at the transitions between the phases. So in particular, in a transition from an ordered phase to a disordered phase, the critical degrees of freedom should be the fluctuations of the order parameter, naturally. And again, there are some apparent exceptions to this. Perhaps not the most obvious are direct transitions between states that break different symmetries, which are called deconfined quantum critical points. And perhaps more obviously are transitions out of deconfined phases, where there's no local order parameter. So for example, this phase we've been talking about, the deconfined phase of Z2 gauge theory, say in 2+1 dimensions. Here there's the order parameter. Well, okay, there's no local order parameter. And in fact, both of these examples can be understood in terms of symmetries. I don't want to say too much about deconfined phase transitions, but the case that I want to think about is this transition out of the deconfined phase of Z2 gauge theory. This second part of the Landau paradigm says that we should be able to understand the critical theory in terms of fluctuations of the string order parameter. So in this mean string field theory, we were literally trying to build a theory of that order parameter. By Wegener's duality between the 3D Ising gauge theory and the Ising model, this theory is the same as the 3D Ising model. That is, the local data of this transition, the critical exponents, are the same as in the 3D Ising model. And so this logic suggests that near the critical point of the 3D Ising model, there should be some description as a string theory, as a theory of loops. And so let me say a little bit more about that. How are we doing on time? Okay, good. Yeah. So this is what we'll spend the rest of the time talking about. This idea that the 3D Ising model is a string theory is an old one. There's a lot of literature on it, which for some reason or other seems to end around 1994. And there's some reason to hope that it can be understood better. Well, we're going to try to be open-minded. I guess that's that's the first reason. And the second perhaps better reason is that we've learned a lot about non-perturbative string theory since 1994, and maybe some of it we can use. So let's retreat a little bit to 2 dimensions and think about the right way to understand the 2D Ising model. So here's a picture of the 2D Ising model on the triangular lattice. So the red dots are spin up, empty space, empty honeycombs are spin down on the triangular lattice dual to this honeycomb. And the picture suggests that you should organize this sum as a sum over configurations of these blue edges that separate up spins from down spins. So that is, we can rewrite the partition sum of the Ising model on the triangular lattice as twice the sum over loops on the honeycomb lattice, and sum over closed loops on the honeycomb lattice. And the reason that there's a 2 is that if I reverse all of the ups and downs, it doesn't change the configuration of the loops. A small technical issue, which will be instructive, is if we did this instead on the square lattice, there's an annoying thing that can happen, which is I can have a configuration where up and down spins are organized in this way around a single vertex. And this configuration is, how to interpret this configuration in terms of loops is ambiguous. I could either interpret it as 2 loops that are crossing, or I could interpret it as 2 loops that are meeting like this, or 2 loops that are meeting like this. And a useful resolution of this confusion is actually just a sum over all of these configurations, but with a sign, which is the number of self-intersections of the loops, which has the consequence that 2 of these 3 cancel each other, leaving behind just a single one. So on the square lattice, the analog of this formula actually involves a -1 to the number of self-intersections of the loops. And this is the first hint that these loops are world lines of fermions. So you recognize that if you exponentiate that into a sum of connected loops, this is the world line sum for a real fermion in 2 dimensions. Okay, never mind about that. It's fermion. The world lines are fermions. And in fact, we can, in this case, we can be very explicit about making the fermion operators. They're a combination of the disorder operator, the object which flips the signs of the couplings along the links along a whole curve here. It's a disorder operator in the sense that it destroys the order. This operator is independent of the choice of this curve because of the Z2 symmetry. And the familiar duality interchanges the spin operator and this disorder operator. And the object which is self-dual under that interchange is the thing that's a fermion, because when I move this thing in a loop, the spin here necessarily crosses the branch cut, it gets a minus sign. And it's not too hard to show on the lattice that this thing satisfies a lattice version of the Dirac equation. It becomes the Dirac equation near the critical point. Okay, so let's try to do the analog of that for the 3D Ising model. In the 3D Ising model, here's the analog of that picture. The red dots are upspins. These walls are the boundaries of the regions of upspins. Again, we can define a disorder operator. Now it's defined, it's associated with a curve. That is, we pick every plaquette that's inside, that's on a surface bounded by that curve and flip the sign of the interaction. It's independent of local changes in the surface, again, by the spin symmetry. You should think of the surface as a branch cut for the spins. And again, we can define an object which is a combination of the disorder operator and the spins, which satisfies something like a Dirac equation, except it's a Dirac equation for each link on this curve, which is reminiscent of the equations of motion for a Riemann-Never-Schwarz superstring, this sort of physical state condition. And so for this reason, Paul suggested that the 3D Ising model is related to some kind of RNS superstring. There's some issues with this idea. One of them was pointed out by Dissler. He argued that the analog of the self-intersection number in the 2D case is the Euler character of the surfaces. So that is, he claimed that you could rewrite the 3D Ising model partition function as a sum over surfaces weighted by -1 to the Euler character. And just as in 2 dimensions, this is an issue that you can avoid by working on a lattice where each edge touches only 3 faces rather than 4. But the reason I mention this is that it emphasizes the fact that in this string theory, rather than being weighted by some small coupling, high genus contributions have the same weight. That is, the absolute value of the string coupling is equal to 1. So maybe that's a, how to say, that's a challenge, let's say. And so a question that we asked ourselves is whether we could modify the Ising model in such a way that the dual string theory would be weakly coupled. So that is, we want to decrease the weight of the domain walls which have higher genus in the sum. So here's an example of a spherical domain wall. We want that one to be most important. Here's an example of a toroidal domain wall. We want that one to be suppressed by a factor of G string squared. And so this is what we're going to try to do. And there are basically two possible outcomes of doing this, assuming that the modified model still has a continuous transition, which it will. One possibility is that making the string coupling smaller leads to a new universality class, a new kind of critical Ising model where spherical domain walls are more important. And then the other possibility is that it changes the critical temperature but preserves the universality class. I'll let you think about which one you think is more likely. And so here we go. Let's try to modify the Ising model. So here's how not to do it. I'm not going to say anything about that. Being string theorists, we thought maybe it should involve matrices. That turned out to be too overly complicated. In fact, there's a very simpler thing that we could do, which is just change the weights of the domain walls depending on their topology. So that is, we're just going to modify the Boltzmann weights. So W naught is the ordinary Ising Boltzmann weight. And chi here is a perfectly local functional of the spin configuration, which is just the number of faces minus the number of edges plus the number of vertices in the dual lattice that participate in domain walls in the given configuration S. So this is a local Hamiltonian. This chi is a local term we can add to the Hamiltonian and see what happens. So this statement requires a little bit of refinement, which will take us on a little adventure for the next few slides. So I said you just count for each vertex, face, and edge of the domain wall, count how many domain walls it participates in. So yeah, just count of the dual lattice, count how many domain walls it participates in. But now consider this configuration. So here, this vertex clearly participates in two domain walls, right? It's part of this domain wall and part of this domain wall. I don't think anybody could argue with that. But what about this configuration? So this is an allowed configuration of spins, but it has more than two possible decompositions into a configuration of domain walls. And the annoying thing is that this one involves 2 and this one involves 3. So there's an ambiguity. One way to avoid this ambiguity, which I'll call the no touching method, is to add an energetic penalty in the Boltzmann weights to exclude the configurations that are ambiguous, doing the analogous thing to the 2D Ising model, that is basically forbidding configurations, like local configurations like that. You can see it doesn't change the critical behavior. It moves the critical temperature. But this has the annoying property that you have to throw away a lot of configurations. So in doing Monte Carlo, it's rather unhealthy. An alternative possibility, which is a little healthier, is to decide on a decomposition into elementary constituents. So there's 2 to the 8 possible couplings of the possible configurations of the spins, 8 spins around a vertex of the dual lattice. So think of that as a binary vector. I guess that should be Z2 to the 8th. Oh wait, hold on. Sorry, these are configurations of the plaquettes around. There are 12 plaquettes touching a single vertex. This leads to a configuration of the plaquettes. And let's order them by the number of faces that are occupied. So the number of these P's that are non-zero, and choose the bases with lowest weight. So for example, this one that I drew here decomposes into these 2. This one that I drew here decomposes in these 2 because these are the lowest weight configurations. So that can be done, and it can be done in a way that actually preserves all the lattice symmetries. There's only one more problem, which is that not all resolutions of neighboring vertices are mutually compatible. So for example, this configuration here which is sort of manifestly 2 spheres touching each other, was assigned chi equals 5 by our algorithm. And the reason that happened is that there is a disagreement across a vertex about what the configuration is. So there's actually a branch point in the middle of this vertex, which contributes to the Euler character. So the thing we need to do is, for each vertex, record how the faces are connected to each other, and then for each edge, check whether the neighboring faces are compatible. And if not, there's a branch point which contributes -1 to the Euler character. Notice that this prescription actually allows unoriented surfaces. There can be surfaces that have an odd number of triple points, such as this one, which make the Euler character odd. And if you don't believe me that this sort of disagreement between faces leads to a contribution to a 4-pi branch point, which has Euler character -1, an appendix to our paper contains a kit with which you can assemble your own 4-pi branch point by cutting and gluing, and you can see that such a thing is indeed a throat like this, which contributes 1 to the Euler character. Okay, so so we've defined this model, or actually we defined 2 models. We defined the no touching model, where we just exclude the configurations where the domain will touch, and the branch point model, where we use this fancy rule involving branch points. And so what does it do? The first thing we should do is some kind of mean field theory, where we just look at the energy. So phi here is the log of the string coupling. And depending on the sign of beta and phi, we want to either minimize or maximize the area and the Euler character respectively. And so this is something we can do, for example, by assuming some not too big unit cell, assuming that spatial symmetry isn't too badly broken. We can identify which configurations have the optimal area and Euler character, and we can identify order parameters that distinguish them from each other. So for example, in the case of the branch point rules, large beta and basically whatever you want to do with phi says that you want to minimize the area. Large negative beta means you want to maximize the area. Those are ferromagnet and anti-ferromagnet respectively. Large phi means that you want to minimize the Euler character. That means you want a large negative Euler character, which is this so-called plumber's nightmare configuration. Large negative phi means you want to maximize the Euler character, which means you want everything to be spheres, which is realized by this so-called packed phase, where everything is a bunch of spheres. Different colors correspond to different components of the domain rule. So each one of these is an independent sphere. So okay, with those expectations, we can try to simulate this model and see what happens. And basically a reason that we're able to simulate it is because despite, we want to simulate near the critical point, where critical slowing down is a dangerous thing, is because we can generalize non-local updates, cluster updates, to this modified model. Because the modification depends only on the structure of the domain walls, it's not too hard to generalize cluster updates. So that allows us to get around critical slowing down a bit. And so here are some simulation results. On the left is results for the branch point rules. On the right is some results for the no touching rules. And in each case, I'm plotting the Binder cumulant, which is a scale-free quantity, which for different system sizes collapses if you know the critical exponents. If there's a continuous transition and you know the critical exponents, and you can see that these different system sizes lie nicely on top of each other in every case, which is an indication of the presence of a continuous transition. In each case, the critical exponent is the same as the 3D Ising one. So we see that the universality class hasn't changed. The critical temperature changes. The reason that this happens, the reason that we knew this had to be the answer, is that the perturbation we're making of the Ising model is a sum of symmetric, that is Z2 symmetric, local scaling operators. We can in the infrared, we can expand the perturbation in local operators of the Ising fixed point. But the Ising fixed point has only one symmetric relevant local operator, which is the energy operator, which is the one that you tune to go through the transition. And so since there's no other relevant operator, there's really nothing else that can happen. All it can do is move the critical point. And so the really interesting thing is, what is the structure of the phase diagram? And here's a picture of the phase diagram, which is color coded. Red is the amount of ferromagnetic order parameter, green is the amount of anti-ferromagnetism, and blue is some combination of order parameters to indicate the packed phase. And so here's the disordered region, and you can see that the critical temperature of the ferromagnetism varies with the string coupling. And we indeed realize the packed phase here and the plumber's nightmare phase here, as we expect from mean field theory. Okay, so now a question that I'm sure is burning in all of your minds is, well, the reason we tried to do this is because we wanted to make the bare coupling, we wanted to make the string coupling weak. How weak can we make the string coupling? So to diagnose that, let's set beta to 0. So this is when the critical temperature goes to infinity, and ask where, at what value of G string does the transition occur. And so in this plot, you can see that, well, the data collapse happens when G string is 0.6, is 2/3. So this is the smallest we can make G string while preserving the Ising universality class, at least with this modification of the model. So maybe I should emphasize a little bit about what we're trying to do here. So, there's this G string, the coefficient of the Euler character, it's some term, it's some coupling constant at the Ising fixed point. It's just it has some fixed point value, which we can't control, and in fact don't even know how to measure. The thing we're really trying to do is to make the dual string theory, to the extent that it exists, weakly coupled on the way to the fixed point. At the fixed point, we can't control it. Okay, so having done all this work, we felt emboldened to make some speculations about what the worldsheet theory might be. So maybe you'll indulge me for a few minutes in thinking about that. So a question that I haven't really addressed in this discussion of the putative string theory dual of the Ising model is how does the Ising Z2 symmetry act in the string theory? The only thing I said about it is that the string worldsheet is a branch cut for the spin, so that is across the string worldsheet, one acts for the Z2 symmetry. A second hint is that the 2+1D Ising gauge theory, which is obtained by gauging the Z2 symmetry, has fermionic excitations. So the fermionic excitation is the bound state of the E particle and the M particle, the end of the string, and the magnetic flux particle. It's a fermion. And well, if we look at the spectrum of an RNS superstring, of closed RNS superstrings, there's a Ramon-Ramon sector and a never-Schwarz sector, which are bosonic. And the fermionic sectors come from our RNS or NSR sectors. And we expect this worldsheet theory to be unoriented because the strings are valued mod 2. And so in an unoriented closed RNS superstring, this is the structure of the sectors. And in particular, this NSR sector is the one where there's a fermion. And so let's try to identify that with the dion of the Ising Z2 gauge theory. And the relationship between the Ising Z2 gauge theory and the ordinary Ising model is they're related by gauging. So if we gauge the fermion number symmetry to get rid of the fermions in this theory, then we get rid of the fermions, and the consequence is that we end up with two Ramon-Ramon sectors. And there's a symmetry operator, a chirality operator, which distinguishes these two Ramon-Ramon sectors from each other. And the conjecture is that chirality operator is the Ising Z2, and one of these sectors is carries the spin. Okay. Having said that, it's tempting to try to interpret, in light of the developments in string theory of the last 20 years, interpret this conjecture as a holographic duality, namely that the strings in question should live not in the same space necessarily, but in a space with an extra dimension. And at the fixed point where there's conformal invariance, the space should be something like ADS4. There are some immediate problems with this possibility. The first is that the bosonic nonlinear sigma model, whose target space is ADS4, is not a CFT, at least not at large radius. Maybe some of the Ramon-Ramon fluxes on the previous slide can explain what holds the space up. A second problem is that adding just a single extra dimension, just an extra radial direction, doesn't solve the problem of making a critical string theory. The sort of obvious solution of having a space-like linear dilaton in the radial direction has the problem that it violates the conformal symmetry. There's a tension between having a field depend on this radial direction and preserving the conformal symmetry of Landau de Sitter space. There's some possible resolutions of this. Perhaps the most promising is this notion of a composite linear dilaton, where the operator that absorbs the Weil anomaly on the worldsheet is not just a single field, but rather some composite operator that nevertheless shifts under a worldsheet scale transformation, namely something like the ADS kinetic term, which is invariant under the target space scale transformations and roughly has the form of the operator that we described earlier. Now, the only problem with this is that it requires me to define log of the derivative of the worldsheet field. And what the heck does that mean? Well, the context where that means something is if we expand around a large flat domain wall, that is a long string. So we can ask about the string theory that governs the fluctuations of such an object. And if large and flat means that it's mostly proportional to sigma, it's stretched in this direction of the worldsheet. And so dx is non-zero, and log of dx squared means something. And this perspective actually has been applied in the past in the Ising gauge theory. For example, in this paper, where the fluctuations of such a string away from the critical point make a prediction for the behavior of this ratio of Wilson loops, which actually is confirmed pretty dramatically by their simulations. Relatedly, my colleague Julius Kuti did some studies of the spectrum of a domain wall in the 3D Ising model. Again in the ordered phase below the critical temperature, and found a gapped breathing mode on the worldsheet. It's something, there's a domain wall, and the thickness of the domain wall is something that can oscillate. And this point of view that, well, I claim that closer to the critical point, the theory is becoming scale invariant, this mode should be gapless and should be the Goldstone mode for the breaking of the scale transformation by the profile of the wall, just as the coordinate fields x on the wall are Goldstones for breaking of translations by the wall. And so this mode should be the bulk radial coordinate. So I claim that this mode that Julius found actually is some evidence that this is a holographic description, at least in this effective string theory of long domain walls. So let me wrap up. So this proposed duality is it's puzzling in several ways. So probably, maybe I should emphasize, we shouldn't be too dogmatic about exactly which strings are related to the, which objects in the CFT, in the spin system are related to the strings. There are various possibilities. And in particular, it may be that under coarse graining, the effective string is actually some kind of coarse grained object with, so-called wall-full handles with a genus-dependent tension. And then there are other objects in the lattice model also that we could consider as candidates for the strings. Notice that this is a pretty weird object. It's an unoriented string theory that doesn't have an open string sector. There's no space-filling D-branes. Such things actually exist, to my surprise. They were written down recently by these folks. But there's a puzzle, I think a rather difficult puzzle, about such duality, which is string theory in flat space has a Hagedorn growth of single string states at high energy. That's something we know pretty well. This works out in ADS-CFT because in a large N gauge theory, there are many, many words made of these adjoints that we can make. This matches the Hagedorn growth, but our weak coupling limit here doesn't involve any large N. And so basically the only way out is if large curvature of the target space removes the Hagedorn spectrum of the string theory. Okay, so let me close just by advertising a mystery that we found. So this is, in some sense, just a byproduct of this study. It's a mystery about the ordinary 3D Ising model, which is the following. So we measured, as part of what we did, we had to keep track of the Euler character, of course, of the domain walls. And so one thing we did was we measured the average Euler character per cluster. So keeping track of which clusters were connected to each other. It has the property that at 0 temperature, it goes to 2, everything is spheres. At infinite temperature, it goes to -infinity, everything is a big mess. And so this thing is it's a non-local observable, but it's computable. Whoa, hello. Let's try that again. Okay, and this is what we find. So this is for the branch point theory. This is for the no touching theory. They're basically all the same. The thing I want to point out is, so the crossing of these curves is the critical point. And this red line in each of these pictures is 0. So you'll notice that the place where these curves cross 0 is the critical point. So for some reason, the value of the Euler character at the critical point, the average Euler character per cluster, seems to be very close to 0. And at least in the ordered phase, the fluctuations are pretty small. And so we noted this observation in our paper, and we got an email from David Hughes saying that people had noticed this kind of thing before in the 90s in a model like our no touching model, and had looked more closely at sort of higher resolution simulations. And actually the thing they were studying was chi itself and not chi per cluster. And they found that it didn't cross. So this couldn't have had a crossing because there isn't such a local scaling variable with small dimension. But we still had some hope that chi per cluster would have a crossing. And so we did a more careful study. And starting from one of these pictures I showed before, we zoomed in a bit near the critical point. We zoomed in a bit more, and we zoomed in a bit more, and it looks like it actually doesn't cross right at 0. This is a bit of a mystery. And so the next thing we did, so the question that it seems to raise is the 3D Ising CFT made of donuts, right? Is it all genus 0 surfaces? And so the next thing we did was make a histogram of the fraction of clusters, the number of clusters with a given chi on average. And it turns out that at the critical point, that distribution looks like this. So here is 2, this is spheres, there's a gigantic spike here at chi equals 2. And then there's a peak at some large negative chi that depends on the system size. And in between, there's nothing. So actually, there aren't that many tori in this picture. And maybe, you know what, I can't resist showing this movie. We made a movie. Wait, where did it go? There we go. Here's the movie. So this is a history as I vary the coupling from as I vary the temperature from the disordered phase past the critical point into the ordered phase. So there's a big spike at the spheres that's not shown because it's too big to show. And as you cross the critical point, that spike and the one that's moving in from large negative chi from high genus surfaces merge. So it's not that there are lots of tori, it's that something more interesting is happening, and we don't understand what it is. This is purely a property of the ordinary Ising model, nothing to do with this modification we made. And I would really like to know whether there's some universal fact that distribution is exhibiting. It happens for both of our microscopic regulators of the theory, and I'd very much like to understand it better than I do. Okay, so final comment is Landau was more right than we thought, and this seems to be a good idea to take him seriously in a context where we have the opportunity. We seem to be learning something, still learning more from it. So thanks for listening. Sorry for going over time.
Yeah, thank you very much, John. Do we have questions?
It's a silent. I have perhaps more of a suggestion.
Right.
Yeah, it's something that kept us busy for a while, and I admit complete failure. And that's the brother of the 3D Ising, right? So you basically say, okay, 3D Ising. We have this equation developed, right, and we can discuss those domain walls, right, and then we try to write down a series of these domain walls explicitly, right, and it was all very interesting. But when you go to 4-dimensional XY, so U1, global U1, you have actually a very similar situation, right? So the vortices are strings. And they can insist that duality should be universal, right? So the disordered phase should be a condensate of these vortices in the same sense that it's an Ising.
I guess one important difference there is that there the strings are oriented. I mean, it's a detail, I guess.
Yeah,
I agree.
there are more differences, right? So a difference is, of course, the fact that the embedding dimension is now 4. So you have to think a bit different about how you build your vortex configurations. And very importantly, the ordered phase is compressible, right? So in Ising, you go from incompressible to incompressible. In XY, you are dealing with a Gaussian boson in the ordered phase. I don't know how to address that in a dual stringy language. And last but not least, the critical point is at the upper critical dimension, right? So it's eventually a free fixed point, and now you have to figure out how your effective description can actually get to a free fixed point.
Mhm.
So I think it's sort of a natural continuation. I think it said, Ising, please, this is the next one to have a look at, because it's really sort of super susceptible to the same technology that you're developing here.
Mhm. Yeah, I agree. I definitely agree with the spirit of your
I
remark.
can even send you a reference to the paper where we admitted our failure. That may give you some insight. Admittedly, you know, somehow too primitive. We didn't get further than guesswork.
Sure, great. Yeah, I'd love
So
to
I
see
do
it.
that, and we have something to look at.
Great.
Okay, thanks for the question. The next in line is Nat. Please unmute yourself.
Hi, John.
Hi, Nat.
I was just wondering, the modified model you wrote, is there any relation with like the double semyon model? Because I noticed that for the double semyon model, you can write the wave function as like where the loops are weighted by the Euler characteristic inside.
The double semyon model, I thought it was -1 to the number of loops. Is that right? So,
Right,
yes.
right.
So yeah, there are topological phases. I guess they're SPTs, where the wave function involves a phase with -1 to the Euler character
Of the down spins and closing that loop, I guess.
Yeah.
Yeah, of the dual of the double semyon.
Yeah, the double semyon itself, though, I think is a simpler invariant that's involved. It's just the
Right,
number
right. I was just wondering if there's any relation with what you're considering here.
Yeah, so I guess right. So I think a very interesting question is, so this Distler observation about the sign of the string coupling is pretty interesting. So so he says that the string coupling has to be -1 or negative, and it turns out that sign of the string coupling is related to okay, let me see if I can get this right. In this paper I mentioned by Kaida, Martinez Parra, and Tachikawa, they construct various kinds of unoriented strings, and the thing that they're varying is they're attaching to the worldsheet theory some 1 + 1 dimensional symmetry protected topological phase. And there's some classification of such phases, and for different choices of elements of that classification, they get different string theories. And one of those choices, which I think it's something like I forget exactly which it is, but in the unoriented theories is exactly whether the string coupling is plus or minus. So I think, yeah, so I think that sign actually has an interpretation as a SPT on the world sheet rather than as a topological thing about the space-time. I'm not sure exactly what it means about the space-time, but it definitely has that interpretation on the world sheet. This choice of plus or minus sign of G string also appears in the recent work on the tenfold way of JT gravity by Stanford and Witten, where so amongst these 10 symmetry classes of matrix ensembles, one of the choices involved in that classification is whether the dual theory has positive or negative string coupling. It's the same kind of thing.
Okay. Do we have more questions or follow-ups, comments? All right. If that's not the case, then first of all, thank you, John, again. Thanks to everyone who asked questions, kept this lively. And if John and maybe Nabil, you want to stick around for a little bit, what we try to offer is to have something like a seminar hangout after the seminar here. So like that's the idea. Anybody who wants to ask informally, I will stop the recording now, and everybody is of course free to go or to stick around. Thank you, everyone.
Thanks.